Hi, this is the read aloud for Chapter 4, Lesson 3, Monitoring Earthquakes. This is the United States. We live in Michigan. The Planet Diary says a whole lot of shaking going on. And the ground moving, is the ground moving under your school? A project that will monitor shaking underneath the entire nation might help you find out. In 2004, so 16 years ago, scientists in the U.S. Array project placed 400 seismographs, all these dots, across the western United States. Every month, 18 seismographs are picked up and moved east, leapfrogging the other seismographs. The map below shows one arrangement of the array. The seismic data that are obtained will help scientists learn more about our active Earth. There's a plate underneath this continent that goes around here. And so there's lots of earthquakes and volcanoes that happen over here. A lot of movement on the the west side of the United States. This one just talks about the epicenter, how they overlap, and they find the focus, where it starts. So page 137, how do seismographs work? Today's seismographs are complex electronic devices. Some laptop computers and a car airbag contains similar devices that detect shaking, but a simple seismograph, like the one in figure 1, can consist of a heavy weight attached to a frame by a spring or a wire. So look at the picture on the side. A pen connected to the weight rests its point on a drum that can rotate. We saw some of this in our Bill Nye Science Guy video, if you watched that the other day with us. As the drum rotates, the pen in effect draws a straight line of paper wrapped tightly around the drum. Seismic waves cause a simple seismograph drum to vibrate, which in turn causes the pen to record the drum's vibrations. The suspended weight with the pen attached moves very little, and this allows the pen to stay in place and record the drum's vibrations. Measuring seismic waves. When you write a sentence, the paper stays in one place while your hand moves the pen. But in the seismograph, it's the pen that remains stationary while the paper moves. Why is that? In seismographs, all seismographs make use of a basic principle of physics. Whether it is moving or at rest, every object resists any change to its motion. So a seismograph's heavy weight resists motion during an earthquake, but the rest of the seismograph is anchored to the ground and vibrates when the seismic wave arrive. So this piece, this weight, does not move. It wants to stay stable, but the rest of it shakes and vibrates when the land, like this, moves. I learned that from Bill Nye. So recording seismographs. In a simple seismograph, a pen's attached to a suspended weight, and it records the waves. I can draw in this for you really quick. So I'm going to start out with a small earthquake, and it will get bigger. And then sometimes it slows down, and sometimes this shaking can be very close. So I drew all kinds of different small vibrations, wider shaking. These are smaller ones too, but you can see that there's more power in them, and these ones are very fast and strong. So that's kind of what it would look like. And did the same thing here on this side. These are P waves, primary waves, secondary waves, surface waves. Primary waves are, remember, those only go like an accordion. They go this way. These waves go sideways and on an angle. And these ones are the rolling waves. They bend the land. These are the fastest. These ones arrive shortly after. These produce the largest disturbance on a seismograph. Reading a seismograph, you have probably seen the zigzagging lines used to represent an earthquake. The pattern of lines, called a seismograph. In the record of the Earth's seismic waves produced by a seismograph, study the seismograph in figure 2. Notice when the P and S waves and surface waves arrive. The height of the lines drawn by the seismograph is greater for a more severe earthquake and earthquakes closest to the seismograph. So, we will turn to page 139. What patterns does seismographic data reveal? Geologists use seismographs to monitor earthquakes. Other devices that geologists use detect slight motions along faults. Yet, even with the data from different devices, geologists cannot yet predict when and where the earthquake might strike. But from past seismographic data, geologists have created maps of where earthquakes occur around the world. The maps show that earthquakes often occur along plate boundaries. Recall that where the plates meet, plate movement stores energy in rock that makes up the crust. This energy is eventually released in an earthquake. Earthquake risk in North America. Earthquake risk in, sorry, I lost my spot. Earthquake risk largely depends on how close a given location is to a plate boundary. And that's what I said over here. This purple is high risk because there's a crack in the two plates right underneath where California is. Washington State and Alaska. I'm sorry, close to plate boundary. In the United States, two plates meet along the Pacific coast in California. Washington State up there and Alaska, causing many faults. Frequent earthquakes occur in California where the Pacific Plate and the North American Plate meet along the San Andreas Fault. That's the movie that we're watching tomorrow. In Washington, earthquakes result from the subduction of the fault. Remember, subduction is when one goes underneath. In Washington, earthquakes result from the subduction of Juan de Fuca plates beneath the North American Plate. Recall that during subduction, one plate is forced down under another plate. Take time and look at all the places on the map if you can recognize any of them. See where we live, we don't have any major plates, so we have very low risk where we're at. So this is interesting. Try and see if you can find some of the cities. Page 140, earthquake risk around the world. I love this map. This is one of my favorite right here. Earthquake risk around the world. Many of the world's earthquakes occur in a vast area of geologic activity called the Ring of Fire. In this area, plate boundaries form a ring around the Pacific Ocean. So that will be on the other page, unfortunately. Oh, I'm so sorry. Here you go. I'll take off the words and I'll let you look at the picture. Around the Pacific Ocean. So here's the Pacific Ocean. Here's our Ring of Fire. Lots of volcano eruptions around here because those plates shift and move, and then the lava can come up from underneath. That magma can come up from underneath. Volcanoes as well as earthquakes are common along these boundaries. The Ring of Fire includes the west coast of Central America and the west coast of South America. Strong earthquakes have occurred in countries along these coasts where plates converge, go together. Across the Pacific Ocean, the Pacific plates collide with several other plates. Here, Japan, Indonesia, New Zealand, and New Guinea are seismically very active. One of the most powerful earthquakes ever recorded occurred off the coast of Japan on March 11th, 2011. It's close to your guys' birthdays, isn't it? No, it's not. I'm kidding. India, China, and Pakistan also have been struck by large earthquakes. In this area of the world, the Indo-Australian plate collides with the Euro-Asian plate. Earthquakes are also common where the Euro-Asian plate meets the Arabian and African plates. So the orange are the plates that are underneath the continent that move slowly and forever. That is the end of our chapter. Please take time to look at the pictures. I always find them so interesting. This is Alaska over here, and all of these are like earthquakes and stuff. So lots of movement around there. Thanks for following along. We'll do the quiz shortly after.